We're going to continue Governance Week. I promised we would get increasing specificity on governance as we went, and we couldn't be more delighted to have Bailey Flanigan here, who will be joining the MIT Political Science Department as well as the MIT CS Department next year. Bailey, please take it away.
Awesome. Thank you. Okay. Hello, everyone. My name is Bailey. I'm a postdoc at Harvard right now, and I'll be at MIT next year. My email is here. Feel free to reach out to me if you have any questions. Okay, so today I'm going to be talking about sortition, which is a way of kind of choosing political representatives who will then make decisions on behalf of a larger population. And my PhD is in computer science, so a lot of this work is going to be pretty algorithmic in nature, despite the fact that a lot of the ideas that motivate it are very governance-related and founded in politics. Okay, so this talk is going to cover 4 papers. I'm not going to cite them during the talk because it would be way too cluttered. So if you're curious about where this stuff is coming from, these are the papers where you can find the results. But here are my lovely co-authors, who some of them are on many of these papers. These are all lovely people. I encourage you to meet them at some point. So just to give you like a little bit of flavor of what's in here, these papers are like generally based in theoretical computer science. So most of the results that I'm going to talk about, even when I don't prove them, are based on things that we've proven. A lot of the claims that I'll tell you are also verified empirically in real data from citizens' assemblies. So just to open the box a little bit on the foundations of what I'm going to tell you, because I won't have time to be specific about every single claim. So the premise of sortition is very old. It's just the idea that maybe in some cases we want to randomly select a subset of the population to be decision makers for that population. So what this looks like, you're going to see a lot of diagrams like this. You have a set of willing participants. In the standard conception of sortition, the willing participants are just the entire population. And what you do is a uniform lottery over the population, just like choose every person independently with equal probability, and whoever gets chosen winds up on what we're going to call the panel, which is the group of decision makers. And what happens in a governance context when we use sortition is that this panel will then convene for like several days, and they're going to learn from experts, they're going to deliberate with each other, and maybe at the end they vote or they come up with some kind of policy proposal. This is not just like a theoretical idea. This model is being used right now around the world in things like citizens' assemblies, citizens' juries, deliberative polls. I'm happy to talk to you about the democratic applications of this more at the end if you want. I'm trying to focus this talk a little bit more on the method of sortition, though, because I think it might be useful for the context of blockchain applications. To give you a little flavor of maybe how this can be used, I have some examples, which Andy so kindly provided to me, about how sortition is already being used in the blockchain in a similar way to how it's been used in practice. So the Optimism Collective in 2024 ran a deliberative process that looked a lot like a citizens' assembly. And it was actually run by people who typically organize citizens' assemblies for governance applications. So the connection is actually somewhat close. I don't know a lot about the details of this process, but the question that they were answering, I think, is a good example. What they were trying to determine together is how they should define, basically, and measure as a formula profit. And so kind of the high-level takeaway here is like, these kinds of processes can be pretty useful for cases where you have to make subjective judgments that affect the whole community. It was also used in 2023 by Cosmos in a citizens' assembly. In this case, they were thinking about what process and principles should drive handling like chain changes to the atom economic zone. Just to kind of give you someone else's much more perhaps informed perspective on how sortition might be useful on the blockchain, this is a quote from the Discord discussion on the Optimism Collective about their process. And they say that we think a deliberative process could be useful in setting collective definitions and shared values, preventing gridlock, and coming to a collective consensus on complex topics. So maybe this gives you a perspective on how it can be used. I think the use cases are perhaps broader than this, but that's something that we can talk about together. So this was a little foray into the blockchain, but back into the world of theoretical sortition. Why do we even like randomly selecting a subset of people? Let's start there. And from here, we're going to talk about kind of the ideas of a lot of political scientists who have been thinking about this for decades in the context of governance. So one reason that this is pretty attractive, here's a quote that reflects this idea, is that when you do a uniform lottery, your panel ends up reflecting, in expectation at least, a cross-section, really any cross-section of this population proportionally. And we're going to call this ideal. Okay, I have a little picture. You're going to see this throughout the talk, showing that the composition of the group of willing participants, which ideally is the whole population, will very closely resemble that of the panel. And we're going to call this representation. It's the idea that the panel is like proportionally representative on key attributes. But these asterisks here kind of indicate a catch, which is that if your willing participants don't actually look like your overall population, then representation, you're really just representing your willing participants. You're not actually representing the underlying population. This will be like a motivating problem that will appear throughout the talk. So when we say representation, we mean representation in kind of like a normative sense. Like there's some notion of representation that you kind of really care about, and we're going to say that the process is representative if it achieves that notion of representation, not just like whatever arbitrary representation exists among the people who participate. Another idea is based in this like theory of allocative justice. It's the idea that everybody is kind of entitled to a fair chance to make decisions on behalf of the collective. And so we're going to refer to this ideal as individual fairness, the idea that people should all have an equal chance to be chosen. And whether equality is really the right thing in the context of the blockchain, it's unclear, right? Because there's this idea that if you have more stake, maybe you're entitled to more power. And we can talk about that throughout the talk. But for now, we're going to talk about individual fairness as giving people an equal chance to be chosen. And throughout the talk, we're going to represent these equal chances using a diagram that looks like this. So these here are selection probabilities. And what that really is for every person in the pool of willing participants, each person has some probability of being chosen represented by the height of their dot. And the dotted line across the middle shows the average probability. And you can see, of course, why a uniform lottery will also give you this kind of trivially. My favorite reason that sortition is cool is that the randomness can prevent manipulation, or at least it can make it harder to manipulate. This is like an idea that appears in a lot of areas of computer science. Kind of randomness makes it harder for a manipulator to really manipulate a system. This is a quote from Political Science by Oliver Dowling talking about protecting the process from subversion. To unpack this a little bit into formal ideals, we're going to break this down into kind of who can actually subvert the process, because there's actually like two kind of parties that might be interested in doing that. There's the people themselves who might get chosen. You can imagine them paying each other to try to like, impersonate other people and try to increase their chance of being chosen, or you can imagine any manner of manipulation. And you can also imagine that the organizers running the lottery could try to cook the lottery by, for example, choosing a bunch of their friends and then saying, this was random. And so we're going to define the first ideal to address the first issue, which is, we're going to call it manipulation resistance. It's the idea that individuals who might be chosen can't influence anyone's chance of selection by misrepresenting themselves. And you're going to see why misrepresenting themselves is, for the governance context, kind of the relevant kind of strategy space.
Bailey, there's like,
Yeah.
I guess, there's like another kind of manipulation, which is like after you've been selected, some outside force influences your vote. And I guess like historically I've heard of anonymity as like the potential solution to that, like keeping the membership secret.
Yeah, that's what's done in practice in citizens' assemblies, typically.
But then you can't verify that it's representative, right?
Oh, well, okay, actually, that's not entirely true. So if you care about verifying representation on like the fine-grained level of like vectors of attributes, like or covariates, then yeah, anonymity is like ruined. But if you just want to verify, that half the panel was women, half was, they actually do release that information in practice, so you can at least kind of verify that it was balanced on marginal attributes. There is, I think, in several ways, a tension between kind of verification and other things that you might want. So we can talk about that. And then finally, to make sure that, the organizers are not just cooking the books, we want transparency. And we define this to mean that constituents can observe their chances of selection and other people's chances of selection. We're going to kind of ignore this ideal until the very end. So we should really just be kind of thinking of the first three for now. I mentioned this problem before. What if the willing participants don't satisfy representation? So maybe we have some kind of underlying reference population that's 50-50 dark green, light green, and the willing participants are very, very skewed. I think this is like a very likely scenario. And it doesn't have to be the case that we want perfect representation of the underlying population, but we're just going to assume that that's what we want for now. So what we would do in this case is we would try to enforce better representation. So maybe we kind of use some sampling procedure. You can use rejection sampling or stratified sampling, whatever you want, depending on the level of kind of complexity of your representation characteristics that you're trying to satisfy. And you can kind of force that the panel has more of these dark green people. But what's going to happen if you do that perhaps unsurprisingly, is that you can no longer randomize equally over everyone. It's just not possible, no matter what algorithm you use, because on average, the light green people have to get a below average number of seats, and the dark green people have to get above average. And this gets worse the more you try to correct the representation away from what's available among those who are currently participating. So here's our fundamental trade-off. And this little symbol here represents the fact that this trade-off gets worse and worse the more skewed your willing participants are in comparison to who you actually want. All right, so this is just like a fundamental trade-off. And why is this bad? Well, it turns out that lottery equality is kind of like a very important determinant of our other ideals that I originally laid out for you. So if you remember individual fairness, we wanted to give everyone like a fair chance. But clearly we cannot do that, right? And I think one of the biggest concerns here are these really low probabilities. Because if we think that everybody is entitled to some share of the chance, we're just really worried about people getting shortchanged. Yeah.
This is obviously correct. I don't love this ex post definition of representation. Like, it seems to me like if I know all the covariates that matter, it's fine to say that there's this ex post notion of representation. But I think one of the reasons we think that we like this kind of system is that we actually think we don't know all the characteristics that matter for opinions, and we don't want to have to pick and choose which covariates we want representation, because that has all sorts of problems. And that we want something more like an ex ante notion of representation, where we don't have to commit to ex post characteristics that we want balance on. And then we want random selection. And then, of course, if the pool of willing participants is not a random sample of the pool of the, like, that's just a fundamental problem we can't fix. But this exact trade-off really rests, I guess, on this ex post notion of representation, which feels to me like it does a little bit of violence to the motivation for lithocracy in the first place.
Okay, that is like an absolutely excellent point. So, okay, right, so let's say that if we say, you know what, we're just gonna accept that our representation is just gonna be as good as it is among the willing participants, then you're totally right. You basically replicate the perfect intersectional representation of everything you know and everything you don't among the willing participants. The reason that doesn't work in practice, and the whole motivation for this work, is that if you actually ran a citizens' assembly like that, based on who currently participates, it would be so incredibly skewed toward people who are highly educated, people who have more liberal opinions, that people wouldn't really trust the outcome. And so for now, for the current practical purposes, we kind of need to do something to correct the selection bias. Now, there's a few pieces of good news maybe, which is that if you have some understanding of how the observable covariates correlate with the unobservable covariates in your set of willing participants, and there's reason to believe that you might, there tends to be patterns in who signs up, you can try to design your ex ante or ex post probably requirements to try to kind of drag along the representation, at least to some degree, to whatever extent is possible. So we are actually working on that right now because we're super concerned about the unobservables. But I'm not sure if it's possible in practice right now to just throw representation out the window. You kind of have to face this trade-off to some degree, I think. Does that make sense?
Yeah, I'm sure that's true.
Yeah, you don't have to be satisfied. It's your call. But I think that this is kind of what practitioners have told us is important to them. Yeah.
So I'm not following what's the end goal. The end goal is to have a panel that represents the actual population. Is that the end goal? Or is the end goal is to have, in the willingness participants, everybody gets a fair chance? These two seems to be very different.
Yeah, in fact, they're exactly in tension. So what you're describing is kind of like two ends of a trade-off, right? Maybe the goal should be to just get perfect representation to the best degree you can and say whatever about the probabilities. Or maybe you might want to just care about only the probabilities and just ignore representation.
And why would anybody care about this equal probability?
Well, we are just about to talk about that right now. Okay, so the first reason has to do with kind of this entitlement to a fair chance, right? It's kind of, if you think about the really extreme case where you set such tight quotas that most people didn't even get a chance to participate at all, you just couldn't accept them, then it wouldn't really be a random process at all, right? Because if there's maybe only one subset of the entire population that fulfills all of your requirements, it's barely random. And that would be considered undesirable by some people who do sortition. So that's one reason that you care, but I think there's a much more important reason that you should care, which I'm about to tell you right now. Okay, so in practical processes like this, in order to actually enforce representation, we need to ask people to report their attributes. So if you wanna, enforce representation on gender, race, age, whatever, you have to ask people those things, because in practice, practitioners do not have access to kind of like individual level census data where they can just say, you're person number 708, whatever, here's a letter, come participate. It's more like they just send out a bunch of letters, and whoever shows up, they have to ask them who they are. And you can verify some things like geographic location, probably age to some extent, but it's pretty difficult to verify a lot of attributes that you care about, at least in the democratic context, where you might want to stratify, for example, on beliefs about the issue, right? If you're a person who is skeptical of climate change, you probably aren't going to trust a panel on climate change unless it actually contains some climate skeptics. There's attributes that are pretty difficult to verify, and you have to ask. And so what can happen is that people can misreport who they are. So in this example, suppose you're one of these light green people, and you think to yourself, I bet, taking the climate change example, if the light green people are people who are really they really care about climate change, right? They would be super overrepresented then among those who participate. Makes sense? They might say, I bet people who are not concerned are not going to show up. I'm just going to pretend to be one of those people. And now you have a new instance with a slightly different pool of willing participants, and this person has gained a pretty significant amount of chance of participation. And I think even more concerning than that, this probability, if it's pretty high, means there's a pretty high chance of actually choosing this person. And if you choose this person, they've stolen a seat from the dark green group, right? Because they're not truly in that group. So there's multiple incentives to manipulate, to try to steal seats. Maybe someone pays you to try to get on the panel. There's all kinds of kind of schemes that could be cooked up as soon as you can fudge your characteristics. Does that make sense? All right, so this is why you also have to worry about determinism in selection, right? Because as soon as there's some people who are being selected as deterministic, other people might try to impersonate those people. And I don't know if that's possible in the contexts that you study, right? There's so much more verification going on there. That's the idea. So this is why in the practice of governance, you really care about the selection probabilities in addition to the representation. Does that answer your question? Okay. Any more questions?
Also, this is just a quick question on it
Sure.
seems like there is one other margin here for trying to avoid this trade-off, which is if you have the ability, making it worth people's time to do this, paying people to participate, which was a key part of Meta's community forums. The pay was pretty generous. If you could pay everyone infinitely, then presumably you would get willing participation from a very broad set of people, and then you wouldn't have to go down these other roads, right?
You're 100% right. And the algorithms that we're going to talk about will just improve optimally as the representation of your willing participants gets better. So they'll take advantage of improvements. But the other thing that you have to be kind of careful of is if you increase the payment somewhat, but you don't increase it far enough to get rid of self-selection bias completely, you have now really increased the incentives to manipulate, right? Because if you're going to get paid a lot, it just strengthens people's desire. And this has actually happened in practice. There was some sweet incentive for participating. I can't tell you too many details because the practitioners don't want the details public, but there were documented cases of people just kind of trying to impersonate other groups as much as they possibly could to get these incentives. So it is a good solution, but you have to be careful and you probably have to have a lot of money. Okay, so we're facing this fundamental trade-off between the ideals that we originally wanted. And a very natural question, which is kind of getting at what you were just saying, is how should we make this trade-off? But that's actually not the question that we're going to answer today, because that is a really hard question. So we're going to answer a different question. How can we design algorithmic tools that allow us to achieve any trade-off optimally? And this is useful because different contexts will probably require different trade-offs. So that's going to be part one of our talk, is I'm going to introduce an algorithmic framework that basically tries to perform panel selection in a way that strikes any trade-off between these two things optimally. And then in part two, we're going to talk about how do we actually deploy this framework, which is going to be very general, to its full potential, where we will talk about how to actually use it to achieve these two ideals that we cared about in addition to representation. And then I will revisit some potentially useful extensions for the blockchain context. All right, so at a high level, the algorithmic framework intakes a set of willing participants, and it's going to output a panel. It's going to enforce representation, which I will formally define in a second, as a constraint. So that's going to be like ex post guaranteed. Whatever you input as your representation requirements, it will be 100% chance the panel will satisfy them. And subject to those constraints, we're going to optimize the equality of the lottery, which means we're going to make people's selection probabilities as equal as possible. To formally specify this framework, I have to tell you what I mean technically by both of those things. So when we talk about representation, we're going to permit practitioners and users to set quotas, which can be any inequality or equality requirements on any group whose attributes you can observe. So to give you an example, maybe we're selecting a panel of size 20, and there's 2 categories of attributes: the region that you're from, north or south, and your political leaning, left or right. So if you were to impose like the kind of representation that you would impose with actual stratified sampling, you would do this. You would look at every disjoint like combination of these attributes, and you would set precise representation targets on all of them. For now, we're just going to say that the ideal case is that they're all equally split. Okay, this might be good, and you can do this with our framework, but this can be very tight, right? This can be super restrictive, and you can't really add that many attributes until maybe your panel just even isn't big enough to satisfy all of them. And so sometimes, and what practitioners often do, is they'll set like looser and more complicated characteristics that try to loosen up the problem a little bit while still maintaining like substantive representation. So you might, for example, say, okay, I need it to be 50-50 north-south, and I'm really concerned about the combination of people from the south and people on the right, and for people on the north and the left, I'm just going to make sure there aren't none. So you can choose any configuration of requirements that you want of this form. Okay. So then when we talk about what we mean by optimizing lottery equality, we're really talking about something about the selection probabilities. And specifically what we're talking about is we want them to be as equal as possible according to some function f, which is any convex mapping between these selection probabilities and some real number telling you how equal they are. Okay, so f is like an equality measurement. And a simple example of this would be like the L2 norm. So you would take like the L2 norm distance between all of the selection probabilities and the average. That would be an example of a valid equality measure.
So manipulation resistance went away from this discussion.
Totally. The framework is basically just thinking right now about representation and lottery equality broadly. Then we're going to talk about how to use our definition specifically of F, right? Because remember, manipulation, resistance, and fairness were properties conferred by how kind of the selection probabilities look. So we're going to think in the next part about our choice of F and how that impacts those other 2 ideals. Does that make sense?
Yeah, it's not obvious that that's the same as optimizing them together, right? So you're gonna first, like, you're gonna sort of lexicographically care about equality, and then you're gonna say within you're like gonna first lexicographically care about representation, then lexicographically care about selection about equal probability, and then care about
yes, exactly. So we are kind of in some sense privileging quotas. That is more of like a practical choice than anything else, because like it's basically related to kind of how practitioners were already doing things, but you could in principle think about doing it the other way and kind of choosing some measurement of representation on the quotas and then fixing some level of equality as a constraint.
Or something in between. I mean, you're making very stark assumptions about like kind of what the loss function you're optimizing, right? You could, like, you're imposing what a very stark trade-off between these 2 things by the order in which you're doing it, and you could choose another trade-off between them that's in between the 2 lexicographic options.
Absolutely. And actually the framework will kind of allow you to do something like that. So I'm sort of presenting the framework as it is first, and then we can kind of talk about the ways you can use it to flexibly demote or promote the importance of quotas. Like, they are a hard constraint, but because you can set them any way you want, there's ways to kind of explore the space of possible constraints and see at least what equality you get in a smart way. So you're totally right to point that out, but I don't think the framework is so flexible that you can use it in a way that's similar to what you want. But yeah, it's also for technical reasons that we do this. Okay, so now I'm gonna give you like a little bit of insight into how the framework actually works. I won't go into this too much because I suspect that in your applications, the quotas that you're going to probably want to use would not be over that complicated of attributes. And this framework is really designed to handle pretty complicated representational constraints. And so it's possible that you might be able to use like a simpler algorithm. Some of the considerations like for fairness and manipulation or whatever might still be useful. But I won't go too much into how we handle like this pretty nasty combinatorial structure because it might not be that useful for you, but I'm happy to take questions about it. Okay, so the goal here is to control the selection probabilities. And we're going to control that by controlling something called a panel distribution. And so here, I'm just going to ask you for now to suppose that you could write down every single panel in the whole world that satisfies your quotas. You can't, but just suppose that you could. So that's any subset of participants that satisfies the requirements. A panel distribution will be a distribution over those panels, okay? And we're going to sample that distribution to choose our final panel. So we're going to compute a distribution, and then we're going to sample it. And you can see why that will immediately guarantee the satisfaction of the quotas, because everything in the support already satisfies them. There's the little symbol saying that we're going to sample it. Okay, so a very good first guess is that why wouldn't you just want to uniformly randomize over all the panels in the world? Let's see what might go wrong. Suppose we're looking at two people in our willing participants, our blue guy and our yellow guy. The blue person here is only on the first panel, and the yellow person is on all the rest. If we use this panel distribution, the selection probabilities that we get are going to give the blue person almost no chance of selection, and the yellow person almost one, right? Because they're on almost every single panel. And so what we can do to fix this is we can design like a slightly smarter panel distribution. We can just tune it a little bit better so that it balances the selection probabilities of these two people. And this is really the intuition. We're going to tune the panel distribution, and recognizing that each person's chance of selection is just the probability of drawing a panel that contains them, this allows us to control the selection probabilities. Yeah?
Is there an intuition for how you would get to a scenario where the blue person was way less likely to be on a panel that satisfied all the quotas? Is it because they were like, they don't count toward any of the quotas, so it's hard to meet all the quotas with them involved?
That would be like a very simple case where it'd be a problem. I actually think the more interesting and like the more practical case is where there's pretty nasty correlations between attributes that you're controlling. So, maybe you have some like upper quota on some attribute and an upper quota on some other attribute, or maybe a lower one, and there's just like only a very, very specific combination of people who can satisfy all of those constraints at the same time. And so then everybody else who might be used there wouldn't be able to be included or something like that. So it's more about the correlations between the constraints rather than just like individual constraints at a time. Does that make sense? It's like actually kind of hard to think about. When I started this project, I found it really difficult to think about. So this is the idea. This is how the algorithm works. It finds an optimal panel distribution in the sense that the panel distribution tunes the probabilities to be as equal as they can be for the choice of convex equality notion that we're using. But, of course, the actual problem happens here because we can't actually compute the entire support of this distribution. Now, I'll give you like a one-slide description of how we address that problem. So why can't we compute all of them? First, constructing even one of them is NP hard. So finding any panel that satisfies your overlapping demographic requirements. It's kind of like set cover. So it ends up being NP hard. But the good thing is that we can use general purpose computation tools to like find individual panels pretty fast. And these tools in particular are integer linear programming. So what we're going to do, just to give you like a sense of what this integer program is we're going to have this oracle and we're going to say to it, okay, find me a panel that satisfies the quotas. And it's going to give me back some integer indicators, one for every person in the willing participants, encoding whether or not they're on the panel that it chose. All right, so these constraints here are basically just going to enforce that I get a valid panel back. We can also, because we're doing optimization, we can tell it to find like a specific kind of panel. It doesn't just have to be any valid panel. And we're going to use that very specifically in the framework. I'm not going to explain exactly how though. But this is the integer programming oracle that we're going to use to call and find our next valid panel.
So just to be clear, the ILP objective function is not your approximate equality objective function, right? That's just something you tune to generate like more panels as you, yeah, okay.
You'll see the framework all together and you'll see kind of what it's doing.
So the problem as thus far described is like super similar to the problem like an experimentalist or a survey researcher would face, and they would just do some sort of really simple block randomization. What are they missing?
Can I ask what you mean by block randomization? Do you mean like stratified sampling?
Yeah, they'd stratify their sample with covariates, and then they'd randomize within them, and then they'd be done.
So back in the example before, when I showed you those toy example of the quotas, the first example I gave you was exactly that. You basically define disjoint groups. The problem is that in practice, practitioners want to enforce representation on like 35 attributes at once, and their panels are only like 100 people. So if you had to define disjoint groups from which to sample, you would have so many disjoint groups that you wouldn't actually be able to, like, you wouldn't even be able to divide up the available people.
You're saying they'd have a bunch of empty cells.
They would have a bunch of empty cells. Well, let me think about the empty cells you're saying. No, that's not what I'm saying. I'm saying that if you have 100 people and you're enforcing representation on combinations of covariates, which is what you get when you divide people up into disjoint, you basically won't be able to be representative on all of the combinations of covariates at the same time because you just don't have enough seats available on the panel. So you might do something like what they do in matching where they coarsen. Okay, but as soon as you're coarsening, right, you're losing the representation that the practitioners actually would want in practice. And so what this problem...
But you can't have the representation they want in practice, right? Because you've only got 100 seats and you've got more subgroups than that.
Okay, so in practice, what they care about is just something a little bit different than what is achievable with stratified sampling. They want representation on gender and they want it on age, but they don't always care about having it on gender and age, on every combination of gender and age. And so in some sense, what this allows you to do is define like more flexible, overlapping attributes. But the problems are actually not totally unrelated because sometimes in survey sampling, you do impose quotas like these. And the heuristics that they're using, I'm guessing, look like the heuristics that people were using for sortition. And they tend to have pretty bad properties. So anyway, I'm actually working on that right now, so I'd be happy to talk about that more.
When you say impossible, is it just exponential? I mean, is it possible with infinite time?
No, I don't mean computationally impossible. I mean that if you care about representation on every combination of like, let's say you've got 5 categories, each of them are binary, and you care about every possible combination of those attributes, right? You're gonna need a lot of people on your final panel to ensure proportional representation of every combination of attributes because there's just a lot of combinations. Maybe you have a lot of empty cells, in which case you're okay. But if you don't, then...
But what goes wrong with the trivial algorithm of just enumerating every subset of people and putting it into a bin, either like it's a valid panel or it's not? Is there not a function to determine if it's valid or not?
Oh, here, you're asking about this.
Yeah.
Oh, I thought you were asking an extension of this question.
No, sorry,
Oh, sorry.
Unrelated question.
Good. Oh, yes, this is computationally, yeah. If you had infinite compute, you could do this. For sure. Oh, yeah. Okay, sorry. Got it. That must have been a very confusing answer to your question the first time. Yeah. Yeah, totally. Okay, good.
I'm just happy to discover that computer scientists distinguish between impossible and possible with infinite computation. That's new to me. I like that a lot.
Yeah, it's totally possible. Yeah, that would have, but it still wouldn't have saved us a lot of time. All right, so you can't find all of them. So what do you do? Right, because a priori, you might need to find all of them in order to define an optimal distribution, right? You may need to place non-zero probability mass on every panel to achieve optimality. But the good news is that actually that's not true. That's like kind of the first insight that allows us to do anything here. Using Kara-Theodori's theorem, which is like a theorem from geometry, and I'm happy to talk about the intuition here after the talk, it turns out that there exists an optimal panel distribution over only very few panels. So we can find an optimal randomization, in other words, that assigns 0 probability to almost every panel that could ever exist. And sorry, I should clarify, n here is the number of willing participants. And that's in practice like about 1,000 or something. And this is like billions and billions and billions. Okay, good.
And optimal here, you're back to your L2 objective function.
Yeah,
right?
totally.
About optimal, yeah.
Exactly.
Yeah. Or any other objective function. Yeah.
Yeah, any that you choose. That's right. Okay, and the reason for this at a very high level is that even though there might be a lot of panels, you have this like really nice special structure in this problem where the objective function that you're actually wanting the distribution you define to optimize is over a much lower dimensional object of length only n, right? It's the vector of selection probabilities that you're giving to people. So it turns out that you don't really need that many panels to randomize over in order to achieve an optimal randomization with respect to individuals' probabilities. And that's kind of the essence of like Cairo-Theodori's theorem. So now we know that there exists an optimal distribution over a findable number of panels, but we still don't actually know how to find them because Cairo-Theodori's theorem, it just tells us they must exist. It doesn't tell us how to find them. This is actually the technical contribution of our algorithmic framework. And this is the part where you actually use this linear objective in finding panels in basically a smart order and also deciding when to stop when you've achieved an optimal distribution. To give you an overview of the actual framework, you start with some support. These little squares right here are panels. You can just sort of arbitrarily generate an initial set of panels, and you're going to compute the best possible panel distribution over the current support, which might not be optimal. And then you're going to ask for a new panel, and you're specifically going to ask from the ILP oracle. And the way that you're going to use this objective is to basically say, find me the panel that adds the most equality to this distribution. It allows me to increase the equality by the most. Then we define a technical condition, which I won't go into here, but if this technical condition holds, then the algorithm terminates, and we can prove that if the termination condition is met, then the set of panels you've found so far is sufficient to be optimal. And this is what really requires a proof in the framework. And if it's not met, we add the panel to our current support, and we repeat the process until we meet the condition. This is how the framework works. And this is basically column generation, if you're familiar with optimization.
So like in principle, you could do ellipsoid method to do this, I would think, in theory, right? But
I don't think so because
they tend to be duals, column generation.
Yes, they are duals, but the challenge here really in using off-the-shelf column generation methods is that the program is convex, it's not linear. And so we ended up using like KKT conditions to define the stopping condition. I don't think the ellipsoid method would work.
If condition holds terminate, that's where convexity gets used, is in that statement? Yeah.
Exactly. You're basically solving the dual. And in the dual program, each constraint corresponds to a valid panel. So you're adding a valid panel, which corresponds to adding a constraint, and then you're checking some condition. And if the condition holds, then you can be certain that the KKT conditions, which are sufficient for optimality, are satisfied. And then you can just basically infer the rest of the values of the dual variable, or the primal variables.
Yeah.
That's
my guess is you could do it with ellipsoid, but this is much more practical.
Very possible. I mean, right, that might have been why we didn't ultimately go with that. I don't remember exactly. Okay, the bad thing about this algorithm is that it has absolutely no guarantees in the worst case on how many panels you have to generate because it's using a heuristic to find the next panel. But the good thing is empirically, you only have to find about n plus like 150 panels. And so n is 1,000, it's like 1,150, not too bad.
And do you think, is that because there is a theorem that says it's always good and you haven't proved it? Or you think there's a big difference between worst case and average case behavior of the algorithm?
I think there's a huge difference between worst case and average case.
So you think in the worst case it could be really bad?
Yeah.
Okay.
I'm not sure though.
Okay.
But I have no reason to believe that it's good in the worst case. Yeah. Okay. So that is the framework. The idea of the framework is that it allows us to make kind of pretty generic trade-offs between representation and lottery equality. And representation we now know is defined according to quotas, which are imposed as hard constraints, and lottery equality, which is measured by some convex function. It's not any possible trade-off, as you pointed out, because we are sort of privileging quotas as ex post constraints. Then the question is, how do we actually use this framework to its full potential? So the first question is, how should we choose F? And this is what will determine the extent to which we can achieve our other two ideals. How should we design the quotas? This is like a huge question, right? Because the looser we make them, the better we can achieve lottery equality, and we can just move along that trade-off in that way. And then finally, I had mentioned before transparency, the ability for people to understand that the process is really random. And so I'll briefly touch upon that also. Our choice of F is really going to determine the selection probabilities, which determines the extent to which we can achieve these ideals. So the first choice of F that was investigated was presented in the original paper that proposed the framework. And its main priority is fairness. So if you recall, when we think about fairness, we're worried about shortchanging people, chance of selection. And so we, in this paper, defined F to just be the minimum of all the selection probabilities, and we just use the framework to maximize the minimum. This does great on fairness. If you think about defining fairness as the minimum, like pretty trivially, that's like the definition. But we found out kind of several years later, after defining a game theoretic model and thinking about how people might manipulate it, that it's like super, super manipulable. And the reason is kind of simple. It doesn't really care about controlling high selection probabilities. And so if you can guess what combination of attributes is going to allow the algorithm to increase the minimum, and you report those attributes, the algorithm will just drive your selection probability all the way up in order to increase the minimum further. And so you can empirically, even in real data, gain probability 1, like pretty reliably by just misreporting like really simple combinations of attributes that you'd kind of guess. Okay, so that's not so good, but it still like was better than the state of the art. This is deployed, and you can actually use it if you're interested on panelot.org. So it's open source, feel free to check it out. To address the manipulation resistance problem, first in theory, we tried a different objective, which was just minimizing the maximum probability, which kind of makes sense, right? You're worried about high probabilities, so just drop them as low as you possibly can. This turns out to actually optimally mitigate manipulation, but the problem is that it's just super unfair, right? It doesn't care about low probabilities, it just drops them to 0. So it's not practical, it was never deployed. Because,
when you talk about manipulation resistance, this means you're measuring this as the size of increase in probability the worst off person can get from.
We consider 3 definitions. That's one of them, the very standard game theoretic definition. Another definition describes utility instead of as the amount of probability you gain, just as the amount of probability you have after manipulation. So instead of post minus pre, it's just post. And the reason that that matters qualitatively is because that's the chance of you stealing a seat from the group that you've impersonated. So that's a different utility function. And then we consider a third utility function, which is how much you can decrease anybody else's chance of selection. So that would be anybody else's pre minus post. Okay? And this optimally mitigates all of them.
So I think like a game theoretic definition is a little tricky. Like a question you might ask is, assuming people can report whatever they want, what is the equilibrium under the algorithm? That seems like the natural game theoretic way of thinking about this.
We originally thought about that. I think there's a few reasons that that ultimately was not what we went with. The first one is that in practice, you wouldn't expect most people to manipulate. I think typically, based on anecdotal evidence from practitioners, it's like a small fraction of people are willing to manipulate. You could still consider some kind of equilibrium definition, though. But the other thing that happens is if you've got, for example, everybody is misreporting, even if you kind of characterize an equilibrium as like, what will they end up misreporting? How much will they end up gaining? My suspicion is that everybody will end up getting about equal probability, because as long as there are gaps, people will exploit them. But then your guarantees are basically meaningless because everybody has misreported. So I think that is a very damning negative theoretical result. But it's also probably not that practically relevant because it will not be the case that most people are manipulating. And so, based on our discussions with practitioners about their impression of how people manipulate, we considered a more of like I won't use the term, I'll just describe it. Basically, if you think everybody else will be truthful and you have some basic information about who's going to show up, how much can you gain by manipulating?
Just the strategic types are small in the population. Yeah. Relative to that, almost everybody's a truthful type.
We basically just, we characterize our bounds handle like coalitions of varied size, but we just basically assume that the coalition or the individual assumes that they're the only people manipulating. That's the idea. But I agree that the equilibrium is the most natural thing to characterize from a theoretical perspective. Okay, so the obvious question then is like, to what extent can you get both of these things? Can you control the bottom and the top at the same time? And this is a recent paper at EC this year that introduces a new choice of F, which kind of does maybe one of the first things you would try. It just tries to optimize a combination of the objective of the maximum and, in this case, 1 over the minimum probability. So it penalizes both low minima and high maxima at the same time. It turns out the functional form 1 over here is kind of important. If you combine them linearly or you use the log, the gradient isn't strong enough and you can't achieve as good of trade-offs. I'm not going to go into the details on that, but it turns out that this trade-off here, so this basically strikes an optimal trade-off, we prove, and this trade-off is actually very weak empirically. It's pretty strong theoretically, like you can have cases where there's just a fundamental gap between the minimum and the maximum, but empirically you can actually achieve almost exactly the fairness of this algorithm and the manipulation and resistance of this algorithm at the same time using this objective, at least in the data that we have. So that's kind of cool. And this one actually has been deployed. It was just deployed for the first time in Canada. I will briefly talk about this. All right, so how should you design the quotas? It's kind of simple. You have to choose the groups and you have to choose the constraints. Sounds easy enough, but it has a kind of a lot of complicated implications that we still don't really understand. And this is what we're working on right now. The most obvious one is that there are downstream impacts on the quality of the process that depend on who is in the room. This is a much more qualitative question. There's also technical implications on the quality of the lottery. If you loosen the quotas, the lottery can be more equal. Some options here would be to try to flag particularly costly quotas. It's pretty hard to see kind of from the outside if you look at a really complicated quota system, which of these quotas is really causing the problems mostly. And then computing constraints at different trade-off points. So this gets to your question about modulating the tightness of the quotas in a more systematic way and seeing what you can get out of the lottery. And that kind of allows you to move along the trade-off. Inclusion of protected groups. Basically, the worry is that even if you protect groups with quotas very tightly, if your quotas are too tight, they permit manipulation, which can then corrupt the representation of the groups that you were originally trying to protect. So using really, really tight quotas is not necessarily the right way to get to really good representation. Okay, so that's another kind of weird, difficult consideration. Maybe a constructive suggestion would be to flag attributes for targeting misreporting. And then there's also the worry about unprotected groups. If you tighten the quotas too much, maybe you're shortchanging a lot of groups, or maybe it's really actually improving the representation of unobservables. So there's a lot of statistics to do there. Okay, I'll skip the transparency stuff for the sake of time, but if you're curious, you can ask me about it. It's like an algorithmic add-on. And then I have one slide on extensions to blockchain applications, maybe, but you can tell me if you think these are useful. So one thing I was thinking about yesterday when we were talking about this security breach, if you want to call it that, is how sortition-based committees can be used to mitigate security risks. So one reason that these are really nice is that you can kind of, depending on the information that you have, control who is on the panel and then ultimately who votes, right? So there isn't this reliance on people just opting in at any given time to vote. So maybe if there's a controversial decision or some condition is triggered, you need to actually assemble a panel and have a more dedicated discussion and decision process than is typically happening in the wild. What kinds of security are needed? So the security required in this process for the democratic context probably is very different than you would need on the blockchain because the adversaries are totally different. People in the real world do not understand probability, they don't have computational power, etc. Another kind of interesting thing, which you can't really do in the real world in democracy, I would argue, but might be able to do in the blockchain setting, is that you actually can just reweight votes kind of, based on stake or whatever. And now this process gives you kind of two options to reweight power. You can reweight votes in the decision process, or you can reweight the probabilities of actually being chosen. And so it gives you kind of two spectra here to play with on how to determine power in these processes. What kind of manipulation is even possible? Very different things are probably checkable and uncheckable. And what can you even know about people, right? You probably have a lot less information, so it might mean that you need to worry a lot more about unobservable characteristics. And then also what kinds of representation are actually substantively useful for this application. And then finally, kind of an interesting extension of this work, this original process was conceived of to kind of just run once in any given setting. But if you're constantly choosing from the same pool of willing participants, and maybe this willing participants group is slowly evolving, you kind of want to think about how much chance of selection people are getting over time, not just in each event individually. Because if you've got someone who's just always getting shortchanged or always getting selected, that might also be a concern, even if you're doing everything you can in each individual time step to make things as equal as possible.